Hello sir, my name is Sharad Chandra and I'm from Electronics and Communication Engineering, Section C, and my subject is physics. My topic is the interference model design of aircraft in the wind, or we can say how an aircraft flies, how it can fly in a wind. First I would like to explain about the wind turbine design. Wind turbine design is the process of defining the form and configuration of a wind turbine to extract energy from the wind. We can say that a turbine is made in such a way that it can consume the wind around it, and it can turn the mechanical energy into rotation, and it can create some electrical power with help of some DC motor. In 1919, German physicist Albert Betz showed that for a hypothetical ideal wind extraction machine, the fundamental laws of conservation of mass and energy allowed no more than 16 by 27 of the wind's kinetic energy to be captured. The Betz law limit can be approached modern turbine design, which reach 70 to 80% of this theoretical limit. In addition to the blades, design of a complete wind power system must also address the hub, controls, generator, supporting structure and foundation. Turbines must also be integrated into power grids. Aerodynamics. The in the wind turbine, the aerodynamics were in such a way that the wind which was passing through the turbine helped the turbine to capture the wind so that it can rotate and turn the energy into the electrical energy. But here in aerodynamics, it is in the aerodynamics of a plane, it is a slight opposite, we can say. Here we are using the energy to rotate it to the opposite of the wind side, so we can maintain a certain speed and certain so that it can fly in the air. Blade shape, dimensions and are determined by the aerodynamic performance required to efficiently extract energy, and by the strength required to resist the force on the blade. The aerodynamics of a horizontal axis wind turbine are not straightforward. The airflow in the blades is not the same as that away from the turbine. The way that energy is extracted from the air also causes to be deflected by the turbine. Wind turbine aerodynamics at the rotor surface exhibit phenomena that are rarely seen in other aerodynamic fields. Power control. How much power it is required so that we can make a plane fly in the wind. Rotation speed must be controlled for efficient power generation and to keep the turbine compounds within speed and torque limits. The centrifugal force on the blades increases as the squares of the rotation speed, which makes the structure sensitive to overspeed. Because power increases as the cube of the wind speed, turbines must survive much higher winds than those loads from which they generate power. A wind turbine must produce power over a range of wind speeds. The cut-in speed is around 3 to 4 meter per second for most turbines and cut off at 25 ms. If rated wind speed is exceeded, the power has to be limited. A control system involves three basic elements: sensor to measure process, variables, actuators to manipulate energy capture and compound loading, and the control algorithms that apply information gathered by the sensor to coordinate the actuators. Any wind blowing above the survival speed damages the turbine. The survival speed of commercial wind turbines ranges from 40 ms to 72 ms. typically around 60 ms. Some turbines can survive 80 meters per second. Stall. A stall on airfoil occurs when air passes over it in such a way that the generation of lift rapidly increases. Usually this is due to high angle of attack, but can also result from dynamic effects. The blades of fixed pitch turbine can be designed to stall in high wind speeds, slowing rotation. This is a simple fail-safe mechanism to help prevent damage. However, other than systems with dynamically controlled pitch, it cannot produce a constant power output over a large range of wind speeds, which makes it less suitable for large-scale power grid applications. A fixed speed HAWT inherently increases its angle of attack at higher wind speed as the blades speed up. A natural strategy then is to allow the blade to stall when the wind speed increases. This technique was successfully used on many hearts. However, the degree of blade pitch tended to increase noise levels. Vortex generations may be used to control blade lift characteristics. VGs are planned on the airfoil to enhance the lift if they are placed on the lower surface, or the limit maximum lift if placed on the upper surface. Furling. Furling works by decreasing the angle of attack, which reduces drag and blade across section. One major problem is getting the blades to stall or furl quickly enough in a wind gust. A fully furled turbine blade, when stopped, faces the edge of the blade into the wind. Loads can be reduced by making a structural system softer or more flexible. This can be accomplished with downwind rotors or with curved blades that twist naturally to reduce angle of attack at higher wind speeds. These systems are non-linear and couple the structures to the flow flood requiring design tools to evolve to modern these non-linearities. Standard turbines all furl in high winds. Since furling requires acting against the torque and the blade, it requires some of the pitch angle control, which is achieved with a sling drive. This drive precisely angles the blade, which withstanding high torque leads. In addition, many turbines use hydraulic systems. The systems are usually spring loaded, so that if hydraulic power fails, the blades automatically furl. Other turbines are and use electric servometer for every blade. They have a battery reserve in case of grid failure. Small wind turbines over 50 kilowatts with variable pitching generally use system of.
Good morning everyone. Myself, I am B. Sai Vaibhav. I am from CSC, C section, first year, and my roll number is 21951A05G8, and my subject is mathematics, and my topic is on diagonalization of complex symmetric matrix. Coming into the topic, diagonalization of symmetric matrix theorem. A real matrix A is symmetric if and only if A can be diagonalized by an orthogonal matrix, that is A equals to U D U minus 1 with U orthogonal and D diagonal. To illustrate the theorem, let us diagonalize the following matrix by an orthogonal. The matrix is A. The matrix A equals to 1 minus 1 1 minus 1 1 minus 1 1 minus 1 and 1. Here is a shortcut to find the eigenvalues. Note that rows 2 and 3 are multiples of row 1, which means A has nullity 2, so that 0 is an eigenvalue with algebraic multiplicity at least 2. Moreover, the sum of 3 eigenvalues is trace of matrix A equals to 3. So, the third eigenvalue must be 3. Let us find the eigenvalue vectors. Lambda 1 equals to lambda 2 equals to 0. That is A minus 0i. The matrix I1 minus 1 1 minus 1 1 minus 1 1 minus 1 1 is similar to the matrix 1 minus 1 1 0 0 0 0 0 0. Take V1 equals to singular matrix 1 1 0 and V2 equals to 0 singular matrix 0 1 1. They form a basis of the zero eigenspace, albeit not an orthonormal basis. Let us apply Gram-Schmidt to obtain an orthogonal basis, that is W1 equals to V1 equals to singular matrix 1 1 0. U1 equals to W1 by mod W1 equals to 1 by root 2. 1 by root 2 into